In this video, we want to introduce you to the notion of a vector-valued function. Now, we've actually seen them already, because vector-valued functions are essentially parametric equations. Right? The idea here is you've got a function whose input is a real number and whose output is a vector, something in Rn. Now, for the sake of this Calc 3 class, we will be focusing on the output being either a two-dimensional vector in R2 or a three-dimensional vector in R3. So one variable in, I think of this one variable in and two or three variables out. Right? But of course, it could be 4 or 5 or more variables if you wanted, but for this class, we'll stick with just 2 or 3 out. So for instance, here is, this. I want to point out that I'm using function notation, like f of t, but I'm using a vector symbol to indicate that, yes, this is a function, but it's a function that's returning a vector. Right? This is not a number for an output, this is a vector for an output. And so you give me a value of t, I can plug it in, I'll calculate an x-coordinate and a y-coordinate and put those together into a single vector to be my output. And if I look at what I get for all the different values of t, from minus infinity to plus infinity, and I get a whole bunch of different vectors that I drew a picture here. I have just barely see it. We'll zoom in on this in a bit. You can see it better. Looks like I drew a line here. Likewise here, I've got r of t is cos t sine t. And I have a circle drawn there. Again, I'm going to zoom in on those in a minute. Here's a couple of examples with in R3, the same cos t sine t as the previous example, but now I have the z-coordinate being t. And it looks like I got a little spring thing there. It's called a helix. Again, we will zoom in on that shortly. And this last one, which who knows what the heck this is. Anyway, it is got 3 coordinates for output, x, y, and z. So this is from reals to R3. Okay. Now, I think of these in 2 different ways. Right? I think of them as parametric curves, or I think of them as vectors. And of course, a parametric curve is a set of points in the plane or in space where a vector-valued function is giving you a bunch of vectors in 2D or in space. And the way we match those together is we think about take all those vectors, stick them in standard position, so their initial points at the origin, and then just look at where all the terminal points are. So, for instance, let's take a look at this right here. Okay. This is the first example. This is r of t is 1 plus 2t and comma, 3 minus t. It's the first example there. Okay. Now, the black line is the curve which is described by those parametric equations. The blue vector here is just one such vector for one particular value of t. In fact, when I click on this, what you'll see is this runs through values of t from, I think, -7 to 7. And all of them have the initial point at the origin and terminal points out on that line somewhere. And the software just, just hung up. But you can see how it traced out from one end to the other. So to me, the vector function is doing more than just describing that curve, because that curve, that line, is a set of points. But to describe it parametrically is to describe it as a path with a particular direction and a particular speed that you're moving along that path. It's more than just the line. It's the line with a direction, with a speed. How fast are you traveling over it? For instance, I'll do the same curve, but I'll make it go in the other direction here. So now I've got both a blue vector, which is parameterized the way it was before, and a red vector, which is r of t is 1 minus 2t, comma 3 plus a. So what I've done is I've used the same point on the line, but turned the direction vector completely around, right? So where one is oriented to go this way, the other one goes that way. When I click on this to animate, you can see that both of the endpoints, red and blue vectors, are always on the line, but they they move in opposite directions. So I'm parametrizing the same line, but I'm parametrizing it in a different way. And this is very powerful. I mean, if you're trying to describe the motion of something, in space, it's not just the curve that it moves along. You want to know where it is at any time too. I mean, if you're mapping, say, airplanes, right? Airplanes could be on paths that cross, but the planes never collide because one of them goes through first and then the other one comes through second. They both pass through the same spot in space, but because they get there at different times, there's no problem, right? And this is important. More than just the curve, you need to know the curve as an object is moving along it in time. Okay? And that's what these vector value functions are really good at. Okay, so let's stop that. We could do the circle as well there, the second example. Let me show you that one. So here I have the unit circle here, x squared plus y squared equals 1, because I claim that's what the graph of this vector function is. So the blue vector here is following along cos t comma sine t by plugging in different values of t, and it just keeps going around and around the circle. Now, to me, there's two very different objects here. There's the circle, which can be described by the equation x squared plus y squared equals 1, but that's a static thing. That just sits there. It's a set of points in the plane that just sits there. On the other hand, the vector function cos t comma sine t is tracing that circle out time and time again, and it's doing it in a counterclockwise fashion, starting over here at t equals 0. I don't know if that's starting. I mean, it starts at negative infinity, but anyway, it gets to here by t equals 0 and then keeps going around. This is the circle, but it's traced in a particular fashion. What I want to do now is I want to trace it out in another fashion. I'm going to leave the blue curve in there, but I'm going to add in, sorry, I'm going to leave the blue vector there. I'm going to add in a red vector, which will still trace out the circle, but do it in a different way. So here we go. What do you see here? One, I slowed it down a little bit, but this one has the red curve, the red vector tracing out the circle twice as fast as the blue one, where the blue one has the parametric equations xy equals cos t sine t. The red one is xy equals cos 2t sine 2t. It still hits on, the tip of the red vector still sits on that unit circle, but it moves around the unit circle twice as fast. And there's all different kinds of ways that I can describe motion along the circle. I mean, I can get it so that it goes forward and then backs up, and then goes forward some more and backs up, and goes forward some more and backs up. It sort of rocks its way around. And there's all sorts of different things. You can go backwards, you can go fast, you can go slow. You can just sort of not even do the whole thing. You just sort of, go back and forth across the top, but always beyond the circle. These are different parameterizations for the same curve. Vector functions, they describe motion. Let's take a look at those three-dimensional ones. So I want to just click on this one here, cos t sine t t. Like this one, there's definitely some circularness to it. If I look straight down on it, I'm just looking straight down the z-axis, you can see the circle in the x, like it's in the xy plane. But because there's z involved here, z is just t, and so as the x and y are doing their circular thing, z is going from minus infinity up to plus infinity, so that circle gets turned into a helix. This is not a spiral, this is a helix. A spiral is a two-dimensional curve, a helix is a three-dimensional curve. Let's go back and look at the last one here. This has got a cos t and a sine t in it as well, but there's other stuff going on. And in fact, what we have here is we have well, sort of a cross between a spiral and a helix, that as this thing spirals, helixes upwards, it's spiraling outward or inward, right? So looking at it from different angles here, right? You can see when t is down on the negative side, z would be on the negative side, and it climbs. The z just keeps getting bigger and bigger and bigger as it goes up. But what's happening is the x and the y are going around initially smaller and smaller circles until it gets down to the radius 0 circle. Actually, radius negative, right? These are all negative radii. And then you get to the positive radii, so they get bigger and bigger and bigger and bigger as you go out here. There's all kinds of stuff we can do. In fact, the next video, let's just take a look at a whole bunch of different examples and have some fun. So there we go. There's your introduction to vector valued functions.